In this video, we'll explore the structure of the heart. We'll take a closer look at its walls, layers, muscle fibers, and fibrous framework, to understand how each part contributes to the heart's essential function, pumping blood efficiently throughout the body. To do so, we'll start by a general overview, followed by detailing the myocardium, the endocardium, and the pericardium. We'll mention some clinical applications and notes, and finally a conclusion to summarize all the key points. The wall of the heart consists of a fibrous serous sac, the pericardium, which encloses the heart and is composed of two main parts, an outer fibrous pericardium, providing mechanical protection and anchoring the heart in place, and an inner serous pericardium, which includes the parietal layer lining the fibrous sac and the visceral layer, also known as the epicardium, which adheres directly to the surface of the heart and forms the outermost layer of the heart wall. A thick muscular layer, the myocardium, which is responsible for the contractile activity of the heart and varies in thickness depending on the chamber, being thickest in the left ventricle. And a membrane, the endocardium, which lines the inner surface of the myocardium, forms a smooth lining for the heart chambers and valves, and plays a role in regulating myocardial function. We'll start by detailing the myocardium. The heart is a predominantly muscular organ. Its thickness is determined by the myocardium, which is composed of striated myofibers arranged in interwoven and anastomosing bundles. It is a richly vascularized muscle, traversed by the conduction system. All muscle fibers originate from a fibrous structure located at the base of the ventricles, forming the fibrous framework of the heart. The fibrous framework of the heart or the heart skeleton consists of 4 fibrous rings. 2 atrioventricular fibrous rings, with auricular and ventricular borders. Their lateral border correspond to the neighboring fibrous rings and the atrioventricular sulcus. Their medial border gives rise to an extension that extends from the valve and forms its fibrous framework. And 2 arterial rings, formed at each opening by 3 thickened areas or loops of the wall, which correspond to the fibrous leaflet of the valve. Moving on to the muscle fibers of the myocardium. 3 categories of muscle fibers must be distinguished, those of the ventricles, those of the atria, and the conduction or excitatory system, which controls cardiac activity. At the level of the ventricles, the myocardium is composed of 3 muscular layers, superficial, middle, and deep. The superficial layer consists of fibers common to both ventricles. These fibers arise from the fibrous rings and trigons, follow a spiral path, and converge at the apex to form the cardiac vortex. They terminate either within the interventricular septum or in the trabeculae carneae. The orientation of these bundles differs between ventricles, left to right for the left ventricle, and right to left for the right ventricle. These common or unifying fibers envelop and connect the muscular sacs formed by the intrinsic fibers, extending from the fibrous rings toward the apex of the heart. The middle layer, which is the thickest, contains arciform bundles specific to each ventricle, contributing to the chamber-specific contractile function. The deep layer, composed of fibers derived from the previous 2 layers, gives rise to the trabeculae carneae and the papillary muscles. The intrinsic fibers of the myocardium vary in their length and obliquity. The longest fibers, with an orientation closer to the heart's axis, are found at the periphery. And the shortest fibers form the deepest layers of the myocardium. This schematic shows the superficial layer of the myocardium, as seen from the base of the ventricles, with the atria removed. It is based on the anatomical descriptions by Kamina. What we see here is a top-down view of the ventricular mass, revealing the fibrous skeleton of the heart, and the spiral orientation of the superficial myocardial fibers. At the center, we can identify the 4 fibrous rings, each surrounding a major orifice, the aortic ostium, the pulmonary trunk, and the right and left atrioventricular ostia. These fibrous rings serve as anchoring points for the cardiac valves, and provide electrical insulation between the atria and the ventricles. Surrounding these rings are spiral bundles of myocardial fibers. Notice how they are colored red on the left, and blue on the right, illustrating the distinct orientation of fibers in each ventricle. These fibers arise from the fibrous rings and trigons, and follow a helical trajectory, converging toward the apex of the heart in a vortex-like fashion. This arrangement plays a key role in the twisting motion of the heart during systole, optimizing blood ejection. We also see the left and right fibrous trigons. They form the central part of the fibrous skeleton and act as structural junctions between the fibrous rings. Importantly, the atrioventricular septum, seen here between the right atrioventricular and aortic rings, houses the bundle of His, linking the atrial and ventricular conduction systems. Overall, this diagram captures the architectural complexity of the superficial myocardium, where muscular dynamics are closely integrated with the fibrous framework. Together, they ensure both mechanical efficiency and electrical coordination within the heart. This illustration presents the superficial layer of the myocardium, as seen from the apex of the heart. It is again drawn according to Kaminer, and highlights the helical fiber arrangement that characterizes the ventricular myocardium. The most striking feature here is the heart vortex, the central point where superficial myocardial fibers from both ventricles spiral and converge. This spiral pattern is not decorative, it reflects a highly organized muscular system essential for efficient cardiac contraction. On the left, we see the blue fibers of the right ventricle, wrapping around in a clockwise direction. On the right, the red fibers of the left ventricle spiral counterclockwise. This opposing spiral orientation allows the heart to produce a ringing motion during systole, which enhances the ejection of blood from both ventricles. At the top of the diagram, we see the aorta and pulmonary trunk, which mark the outflow tracts of the left and right ventricles, respectively. This helps us orient the image anatomically, with the base of the heart located at the top, and the apex at the center of the vortex. This schematic beautifully captures how the muscular structure of the heart is more than just layers, it is an engineered spiral, designed to maximize both force and efficiency with every beat. And this diagram illustrates the middle layer of the myocardium, based also on the anatomical description by Kaminer. Unlike the superficial fibers, the fibers in this layer are more compact and specific to each ventricle. They form arciform bundles, concentric, curved muscle fibers that wrap around the ventricular cavities. On the left side of the image, in blue, we see the muscle fibers of the right ventricle. These fibers originate from the fibrous ring surrounding the ostium of the pulmonary trunk, and they curve around the right ventricle in an inward spiral. On the right side, in red, the muscle fibers of the left ventricle emerge from the fibrous ring of the aortic ostium. They form tightly packed arcs, which reflect the greater muscular mass of the left ventricle, necessary to generate higher pressure for systemic circulation. This middle layer plays a central role in the contractile force of the heart, providing a balanced and coordinated contraction that complements the spiral movement of the superficial fibers. Together, these muscular structures ensure that ventricular systole is both powerful and efficient, adapting to the functional demands of each side of the heart. Let's tackle now the muscular fibers of the atria. The musculature of the atria, which is thin, is also composed of intrinsic fibers and common fibers. The intrinsic fibers are grouped into two categories of bundles: annular bundles surrounding the orifices, and anciform bundles extending from the upper to the lower part of the fibrous ring. Moving on to another important component of the myocardium. The heart contains a specialized muscular tissue known as the cardiac conduction system or cardionectar system. It spontaneously and rhythmically generates local impulses. These impulses are transmitted over distance, stimulating the remainder of the myocardium and triggering its contraction. This specialized network of muscle bundles and neural elements ensures the coordinated propagation of myocardial contraction. Let's talk now about the endocardium. The endocardium is a thin, smooth, and adherent membrane that lines the interior of the heart. It is continuous with the inner lining of the blood vessels, that is the endothelium. It contains no blood vessels of its own and is nourished by the blood flowing over its surface. And finally, the pericardium. It is represented by a fibrous serous sac that encloses the heart. It consists of two components: an outer fibrous layer and a deeper serous layer. Concerning some cardiac pathologies, a weakened heart muscle may lead to rapid heart rate, the presence of fluid in the lungs, thickening of the heart wall, and swelling of the lower limbs. These symptoms are often associated with congestive heart failure. In summary, the heart is a specialized organ whose structure ensures efficient pumping. Its myocardial layers enable strong, rhythmic contractions, while the endocardium allows smooth blood flow. The fibrous skeleton gives support, and the conduction system ensures a well-coordinated heartbeat. Together, these elements keep blood circulating effectively throughout the body.